Hello guys, welcome to my YouTube channel Code and Canvas, and in today's video we will be learning about segment tree. So the prerequisites of the segment tree are basic understanding of binary tree, how the binary tree works, its architecture, nodes, internal nodes, etc. And array representation of binary tree, how a tree is represented in the form of an array, and the understanding of recursion. As we will be using array representation of a tree in all the operations of the segment tree, so let's quickly go through that. So in this image, as you can see, this is a binary tree. If you will look into this array, this is the array representation of this particular binary tree. If you will look here, the root node is present at the index 0, then its children are present at the indexes 2i plus 1 and 2i plus 2, where I represents the index of the root node. So 3 is present at index 1 and 6 is present at index 2. Similarly, the children of the 3 will be present at 2i plus 1, which will be 2 into 1 plus 1, that is 3, and 2 into 1 plus 2, that is 4. So 1 and 4 are present at index 3 and index 4. As 6 has only one children and right children, so you can see the index 5 is blank because 2 into 2 plus 1, that is 5, it has no element in it, right? That is why the index 5 of the array is blank, or you can say the left pointer of the element 6 is null, and its right children present at index 6. So this is the quick overview of array representation of a binary tree. Let's start with our problem statement. Let us assume we have an array and we want to find the sum of elements within a particular range. For example, we want to find the sum of the elements that belongs to from index 1 to index 5. That will be 3, 6, 1 and 4 and 2. As you know, it's fairly easy to calculate the sum of all the elements that are present within an index range. You can just quickly go through the first index and iterate it to the last index, whatever your range is, and sum the elements accordingly. But the complexity that this approach will take will be n. You have to go through all the elements one by one, right? So for a small array size, it's not an issue. But let's assume array has millions of numbers, and the queries that we have for finding the sum within a range are in millions. For example, let's say we have millions of queries, and each query is has a different range of indexes. Then your time complexity will be number of queries into the number of elements in the array, right? That will be a huge complexity. So to reduce that, segment tree is used. So we will be taking this example only for all the operations of the segment tree going forward in the video. So first, let's understand what is segment tree. Segment tree is a form of binary tree which is used for sorting intervals or the segments. It means it stores results for a particular segment of the array. The result will be depending on your problem statement. For example, if you want to design a segment tree to get the sum of a range of elements in an array, then you will be storing sum in the internal nodes of segment tree. If your problem statement requires to find the minimum element within a range, then you will be storing minimum element in the internal nodes of the segment tree. We will look at this in the going forward in the video. Segment tree is used to perform multiple range queries and also update individual elements or a range of elements within a logarithmic time. We will go into the detail of this when we come into the operations of a segment tree. First of all, there is a limitation with the segment tree. So operations that can be performed in the segment tree must be a binary and an associative operation. Binary operations are operations that require two inputs like sum, subtraction, multiplication, division, etc. etc. Associative operations are the operations for which a plus b plus c equal to a plus b plus c. You can see this example here, right? So sum is an associative operation because no matter how you add these two numbers, the result will be equal. But subtraction is not an associative operation because uh, depending on what numbers you subtract first, the result will be different. For example, if you subtract a minus b first, then minus c, the result will be different from the right hand side. So some of the operations that can be performed in a segment tree are mentioned here, which include obviously sum, minimum or maximum of a queries, or searching the index given a prefix sum. For example, you are given a sum and you want to find the index at which the prefix sum is ending. That you can do with the segment tree. You can counting the frequency of range of maximum minimum. You can find the GCD and LCM, greatest common divisor and LCM within a range. You can also find AND, XOR and OR operations within a range. Or you can, for example, you can also find the number of zeros that are present within a range or the 0th Ethiopian index with the help of the segment tree. So different operations will require different results to be stored in the internal nodes of the segment tree. So let's start with the concepts of segment tree. So here I have taken an array, a small array of size 7. In the blue color, I have representing the index of each array element. So below here is the segment tree for this particular array, which represents sum within a range of elements. So structure of a segment tree is a binary tree structure, and each internal node or the leaf node represents a range of an array and the sum within it. So the root elements represents a range of 0 to 6, basically the whole array. So it will store the sum of all the elements present in the array. So if you will sum all the elements here, 5 plus 3 plus 6 plus 1 plus 4 plus 2 plus 7, it will be 28. It has two children, 15 and 13, which represents the range from 0 to 3 and 4 to 6. So as you can see, if you will sum the elements from 0 to 3, the sum will be 15, which is present in this internal node. Similarly, if we will sum the elements between index 4 to 6, which is 4, 2 and 7, the sum is 13, which is present here. If we go down further, this node represents the range of 0 to 1. This node represents the range of 2 to 3 and so on. The leaf nodes in a segment tree, they represent the actual element. So in a segment tree, internal nodes will always represent a range of always represent a range. For example, 4 to 5, 5 to 6, like that. But all the leaf nodes, they belong to a single element of an array. So as you can see, all the leaf nodes, they are basically this array only. If you will go to them one by one, they are in same order as they are present in the array. They do not represent a range. So every time all the elements that belongs to an array, they will be present in leaf node only. So size of a segment tree, there is an upper bound that is present, which is equal to 4 into n, where n represents the number of elements present in the original array, which is this. So here, as we can see, the number of elements present in this array is 7. Size of the segment tree that can be taken up to 4 into 7, which is 28. This is actually an upper bound. This is not the actual size of segment tree. Actual size of segment tree needed for a particular size that is represented by n will be this, which is 2 into to the power CL of log n minus 1. Let me explain how this formula comes into the picture. For that purpose, we will be taking another example, which is here. Here I have taken an array of 6 elements, and I have created a segment tree based on these elements. So if you will see the array representation of this particular segment tree, you can see some of the elements in between are also empty, which was not the case here, right? These two were empty because 7 does not have any children, right? But here in the middle as well, the elements are empty. This is because of the size of the array, because our elements are less, so it's certainly possible for some entries in the array to be empty in between as well. It depends how your segment tree is built. So here as well, uh, the root node represents the whole array, which says from index 0 to index 5 the sum will be present in the root node. Now we again divide our array into half. So 5, 3 and 6 will go to the left of this root node, and 1, 4, 2 will go to the right of this root node. So 1, 4, 2, the sum of these three elements is present here, and sum of these three elements is present in this internal node. Again, we try to divide our array into half, which is 3 divided by 2 is actually 1, which we round up to 2. So 5 and 3 will go on the left side and 6 will go on the right side. Similarly here, 1 and 4 will go on the left side and 2 on the right side. As 2 does not belongs to a range, so it becomes the leaf node, right? There is only one element it is representing now, so it becomes the leaf node. Similarly, here it represents a range of 3 to 4, which again is divided by half, and 3 goes on the left and 4 goes on the right. So the element 1 in the array and element 4 becomes the children of this internal node, and sum is stored here. So 4 plus 1, 5. Similarly here, as it represents a range of 0 to 1, we again divide it into the half, and 0 index goes to the left and 1 index goes to the right, and 5 become the left child of this 8 and 3 becomes the right child. These two nodes do not have any children, they are leaf nodes, right? And if you will look into the array representation of a tree, a binary tree, you know for a node its children are present at 2 into I plus 1 index and 2 into I plus 2 index. So as you can see, the 6 here it is present at 4th index, right, in the array representation of the segment tree. So its children, which is 2 into 4 plus 1, which is 9, and 2 into 4 plus 2, which is 10, will be empty because it's a leaf node. So it's not necessary the array representation of a segment tree will fill the numbers continuously. There can be gaps in between. So to make up for this, so that we don't get exception, index out of bound exception or any other exception, we take a upper bound, which is 4 into n. Now let me explain the minimum size that it needed for a segment tree. For that, you have to understand the concepts of complete binary tree. So a complete binary tree is a tree in which all the levels of a tree are completely filled. For example, if 6 would be having children, these two nodes, which I have represented in red color, basically the null pointers, they will not be there, right? There will be children for 6 as well as 2. 6 and 2 both will have 2 children. So if you have n number of elements in an array, the depth of the segment tree can go to CL of log n. So I have 5 elements in the array, right? So log 5 is something 2 point something, right? And if you will do the CL of 2 point something, it will be 3. So you can see the depth of this segment tree is 1, 2, 3. Similarly, if I have 8 elements in my original array, again the depth will be 3, right? Because log 8 is again 3. Now if I have 9 elements in my array, then the depth will be log 9, right? CL of log 9, which will be 4, because the log of 9 is 3 point something. So the and in a complete binary tree, if you will go into the details of a complete binary tree, you will know if there are n leaves present in a if there are n leaves present, then the number of nodes that are present as internal nodes will be n minus 1. So for in this example, you can say if this level was full, there will be 8 nodes present, right? 1 2 3 4 5 6 7 8. And if you will count the internal nodes, there will be 7 1 2 3 4 5 6 7. So this is a generic formula. If the tree is complete binary tree and it's all the levels are full, then the number of internal nodes is always the minus 1 of number of leaf nodes. Now you know number of leaf nodes in a segment tree can be equal to the seal of log n, where n represents the number of original arrays, right? So this comes here, seal of log n. Now you know the total nodes present in a complete binary tree will be number of leaf nodes plus internal nodes, right? So total number of nodes that are present in this complete binary tree will be 2 into 2 to the power d minus 1, where d is the depth of a tree, right? 1 2 3. And we know depth can be calculated by using this formula, seal of log n, right? So you got this formula, 2 into 2 to the power seal log n minus 1, which is the same formula here. This is how we calculate the minimum size that is needed for a segment tree. If you don't understand this concept fully, please go through this again. It's important to understand why are we using this formula to calculate the minimum size needed. So to reduce this complexity while coding a segment tree, we just take a safer upper bound, which is 4 into n, because this value will always be greater than this value for a particular value of n. I know by taking this value we will waste some memory, but it will not be much. If you will compare it, the values of this formula and this formula for a very large values of n, they will be almost similar. So we just go with this safer upper bound so that we don't get any exception of index out of bound or something like that while building or performing any operations in the segment tree. Okay, that's it for all the basic concepts of the segment tree. Let's go into the operations of all of the segment tree. Let's start how we construct a segment tree. So this is a pseudo code I have written, and this is the array I have taken as an example. So let's quickly go through this code and let's fill up this segment tree as we go with the flow. So our function will be called on the root node. So initially our array segment tree array will be empty, and we will be calling this function with this array that we have here, 536142. Node start and end. Node will be the value of the index in the segment tree from where we are starting our tree. So as you know, our root node is always present at index 0, right? So initially the value of node will be 0, which I have put here. So for root node, the value of node in this function will be 0. Array will be same for all the nodes. Start and end are the values of indexing of the first element and the last element of the array. So this particular this particular array has 6 elements, right? So start of the array is always 0. It will always be 0. If you are using a one based indexing, then you will be passing the value of start as 1. I have done all my calculations and operation based on 0 based indexing. So I will be putting the start value as 0, and end value will be the last index of the array, which is 5, which represents the value 2. So initially the root node, this function will be called for the root node with node equal to 0, which represents the first element, first index in the segment tree array, and start and end represents the starting and the ending index of the original array. Mid I'll explain while explaining the algorithm. So now if you will go through these steps, our first condition is a base condition, which says if start is equal to end, then do something. In this case our start is not equal to end, so we'll go to else. Now we are calculating a mid here, start plus end divided by 2, which will be 2, because 5 plus 0 divided by 2 is 2. Now we call the same function again, so it makes it a recursive function. So we will be calling the same function again on the children of this root node. You know from the array representation of a tree that the children of the root node will be presented 2 into this particular index plus 1 and 2 into index plus 2, which we are doing here. So the index of this particular current node is present in this node, right? Node variable. So the children of this particular node will be presented 2 into node plus 1 and 2 into node plus 2, which we are passing as a value in the recursive calls for both the children. So for the left part of this, the left subtree will represent the ranges from start to mid, and the right subtree will represent the range from mid plus 1 to end, where start and end are the starting and the ending indexes of the original array. So let's first start with the left part of the tree. So after our first call, uh, this node will call a sorry, this node will call a recursive call to this node. Here we know now the node value has become 1, start is 0 and end is 2, which is the value of mid in the previous node. And here again, as start and end are not equal, the same thing will happen again. So mid will be calculated, which will be equal to 1, and again the same function will be called recursively for both children of this particular node. So first we will go to left. So there will be recursive call to this particular node. Here again the node value will become 3, which is actually 2 into this node plus 1, 3. Start is same and end is equal to the mid value of this node, which is 1. Here again the start and end are not equal, so we will again go to the left. Now if you will see here, because start and mid are same here, which will be passed at start and end in this node, start and end has become equal in this particular node. So this condition represents that it is now a leaf node and no recursive call should be made further. So now this condition has become true, right? So for now, when the condition becomes true, what we are doing, this tree node, this tree array, this represents this segment tree array, which is empty right now. So it says tree of node should be array of start, right? Because start and end represents the indexes in the actual array, the original array, and node represents the index of a segment tree array. So here what we will do, tree of node, which is segment tree of 7, which is here, it will be array of start, which is 0. So 5 will come at the 7, and this node will be filled up with the 5. Now all the operations of this particular node are done because no recursive calls are being made. Now the recursive function will get deleted and the previous function will come into the picture. So the call will go back to the previous parent node, which will be here. Here we have already done with this on this particular node, we are already done with this particular statement, right? Now the right subtree will be called for this node, which is here. So the call comes here, then it goes back, then again it goes to its right subtree. Okay, so here as you can see again, the start and end has become equal and node is 8, right? So here we again go to node 8 in the tree and fill up with the value of index 1 in the original array, which is 3. So let me fill 3 here and let me fill 3 here as well. Now we are done with this node, so we will again go back to its parent node. So both the operations, both these build operations are complete for this parent node, right? The last statement says the value of this particular node will be the sum of its children values, which is 2 into node plus 1, 2 into node plus 2. The sum of 5 and 3 will be put here, which is 8. And here, as we can see, we are in the array representation, we are storing it at a index that is present in the node. As here the node value is 3, so this 8 will be present at index 3 in the array representation. Now this node is done, so the call will be passed to its parent node again, which will be going here. Okay, for some reason these arrows are not working. Yeah. Okay, for this node, now the left part is done, which is the first build operation, right? So now it will go to the next part, which is now it will go to right, which is the next build statement. So as we go here, we say again start and end are equal. So at our segment tree fourth index, we will put the element that is present at index 2, which is 6 at the fourth place. So 4 will put the 6 here, and 6 will be filled up here as well. Now you can say this node is also done, because start and end are equal, so no recursive calls here. It will go back to its parent. So let's go to parent again. Okay, let me try this way. It's not working. So let's go to this parent. Now here both the build operations are done, right? Now this statement will store the sum of its children into this node, which is 8 plus 6, 14. And if we will look into the array representation, this will be stored at node index 1, which is 0, 1, 14. Similarly, now this is done, we'll go back to the root node. So for root node, we are only done with the left part of the tree, right? Now it will go to the right part, of the tree. Here start and end are again not equal, so it will make again recursive calls with the respective values. It will first go to the left. Here start and end are again not equal, then it will be again divided into 2 recursive calls. Now finally the start and end are equal here. So here we will put the array index of 0, 1, 2, 3. 1 will be put here, and index of 4, 0, 1, 2, 3, 4. 4 will be let me try that, put here. In the array representation, 1 will be at index 11 and 4 will be at index 13. I think I made a mistake here. It's not actually 13, it's 12, because 2 into 5 plus 2 is 12, not 13. So let's put 4 here. Okay, now it will go back to its parent node. It will again add the it will store the sum of its child, which is its children, which is 5, which will be present at node 5 in the index 5 in the segment tree array. So it will be at index 5 and 5 here. It will go to its parent. It's done with the left part only. It will go to right. So here we will put the element presented index 5, which is 2. And in the segment tree array, it will come at index 6, which is here 2. Now it will go back to its parent. It will store the sum of its children, which is 7. It will be stored in the array at index 2, which is here. It will again go back to its parent here at the root node. Here it will store the sum of these two, which is 14 plus 7 is 21, which will be present in the array at index 0, 21. So now you can see our segment tree has been built, and if you will compare it with the segment tree present in the top, you can see it's exactly same. So this is how you build your segment tree using an array. So if you will look into the time complexity of building a segment tree, if you will look into this function, for each node this function is getting called, right? But if you will look into this function, this is a these are constant operations. All these operations are not depending on a value of n or running n times like a loop or something, right? These are constant operations. So for each node, the work is constant, and the number of nodes that are present in a segment tree, as we already know, are these many: 2 to power c log n minus 1, which we simplify to an upper bound, which is 4 into n. So for each node, the work is constant, and the maximum number of nodes that can a segment tree have is 4 into n. So our complexity is 4 into n. In a complexity, we remove all the constants and everything. So our complexity will become big O of n while building a segment tree. Big O of n. Similarly, space complexity will also be big O of n, because the maximum space that we need for a segment tree is 4 into n. If you want to understand why are we removing constants here, you can check my video on asymptotic notations. Now let's move to another operations of a segment tree, which is updating an element in the array. So we have the same segment tree present here. I've already built it, and now we want to update, let's say, element which is present at 6. This element we want to update it to 10. So element that is present at index 2, which is 6, we want to update it to 10. So now we call this function with all the necessary values, where node again represents the uh, index of the array for the current node for which the function is getting called. So initially the function will be getting called to the root node. So initially the value of node will be 0, because root node is always present at index 0. Start and mid are again the starting and ending index of the original array, and mid is calculated as we calculated in the build operation, right, within the algorithm. So let us start. For all the calls, all the recursive calls as well as the initial call, the value of I is equal to 2, which is the index of the element which we want to update, and v is the new value that we want to put at index 2. For example, we want to update this 6 to 10, right? So value of v is 6. So similar algorithm here, again if start and equal to end, then we do something, otherwise we again do something else. Here again start and end are not equal, so we go in the else part, where we calculate mid value, which is start plus end divided by 2, again it's 2. Now we check if the mid is less than equal to I, then we do something else, we do something else. So you need to understand here, we want to update the element that is present inside the index, right, which is at 2, right? Now a node of a segment tree represents a range. The root element represents the whole array, but its children represents one half of the array, and the other children represents another half of the array. Now we know the index 2 will be present in the left subtree of the root node, right? Because the left subtree represents the range from start to mid, and the right subtree represents the range from mid plus 1 to start. So index 2 will be present in the left subtree of the array. So that is what we are doing here. If the index that we want to update is less than equal to mid, then we go to left, otherwise we go to right. Here we are again passing the index of the children, which is 2 into node plus 1, 2 into node plus 2, and the ranges that is represented by the that particular node, and the value of index and the new updated value. So same thing will happen here. Again here actually start and end are not equal. Again we will calculate mid is equal to 1. Now we know index 2 is greater than mid, so we go to right. Here now start and end has become equal, so we have found our node. So now we will update it to 10. Let me update it to 10, which will also update it into the index 4, which is represented by this node variable in the segment tree array. So at index 4 in segment tree, we will update it to 10. Right now we come back to the parent node. So in the parent node, after this if else operations is done, what we do, we update the value at parent as well, right? Because our leaf node got updated, because leaf node represents the original array values, right? So if they get updated, the uh, s- result that will be present in internal node, uh, all the internal nodes that come between the root node and the that comes in the path and from the root node to that leaf node will be updated, right? Because this internal nodes represents the sum of its children, right? Which is now 18, which is not 14 anymore. So this will be updated to 18 at index value 1 in the segment tree array, which is here. Again we go back up. Now again we update the sum of the root node, which will be 18 plus 7, which will be 25. This will be updated in the array as well. So this is how the update operation is performed in a segment tree. You can see the complexity here is again log n, because at max we are traversing at max um, we are calling only one node at a particular level, and the maximum depth that we may go is the height of a tree, which is represented by log n. So the time complexity here is big O of log n. Now let's come to the last operation in a segment tree, which is querying a segment tree. Now after updating a value or building a segment tree, we want to get the sum between a particular range. For example, I've taken a range of index 1 to 4, which is from 3 to 4. So we want this sum 3 plus 6 plus 1 plus 4. How do we get this from a segment tree? So again, this is a pseudocode that I have written. It's not a actual coding actually. It's not written in any language. It's just a pseudocode. So again, this function will be initially called on the root node. I have written all the values here. Node will be again 0, which represents the index of this root node in segment tree array. Start and end again represents the same. The starting and index, starting and the last index of the original array. Mid is calculated between in the algorithm, and p1 p2 will look. So let's start. Now there are three three cases that can happen when you query a segment tree. First, the range that is represented by that particular node, that will have conflict between the range for which you want to query the segment tree. For example, root node represents the whole all the whole array, right, which is 0 to 5, but we want the result from the range of index 1 to index 4, right? So there is a conflict. uh, so in case of conflict, we make two recursive calls to both. The node will make the recursive calls to both of its children. So as you can see, these two conditions are not true for the root node, because R and L represents the range that we want to query, and start and end represents the range that that particular node represents. So these two statements are not true for the root node, so it will calculate the mid, which is again 2, and query like we are doing the same in update and build operations with the children node and start, mid, and L and R. Now first let's go to the left. Here start and end are again conflicting with the range that we want to query. So it will again make the recursive calls to both of its children, which will go here and here. Let's go to the left. Here start and end are again conflicting. So it will again make a call to both of its children, which is here and here. Now again go to left. Here you can see the start and end is out of bound with the range that we want to query, because we want to query elements between 1 and 4, and this node represents the range. It represents only a single element, which is 0, which is not part of the range which we want to query, right? So we will return a default value here. So for sum the default value is 0, right? Similarly for if you want, if you are calculating the minimum number between a within a range, then the default value will be the smallest number possible, right? So in case of sum, as the default value will be 0, but will because it will not have any effect in the sum, we are returning 0 here if there is no overlap between the two ranges. So this is our first base statement. Now it will come back to the parent node. As you can, the first query here was made on the left subtree. So the result will be stored in P1 for this parent node. For this parent node, which represents this 8, it will be stored in the P1. So P1 will become 0 because this node returns 0 here, right? So P1 will become 0. Now it will query its right subtree. 2 into node plus 2, mid plus 1 and LR. It will query the right subtree. Here we can see the range this node represents is completely under the range we want to query, which is our second condition, complete overlap. So we return the value present in that node. So here we will return 3, which will be stored in P2 here, right? Now this node will return the sum of values that it got from its children, which is 0 and 3. So 3 plus 0 is 3. It will return 3 to its parent node, which is 14. So the 3 will be stored in P1 here. Now the second recursive call will happen for this node, which will go to 6. Here you can see start and end. This particular range is completely inside our queried range, right? So again the same thing will happen. The value of node will get returned, which is 6. So here P2 will become 6. It will return the sum of P1 and P2, which becomes 9, and 9 will be stored in P1 of its parent node. Now same thing will happen. It will go to its right subtree. Here you can see start and end, right? This is not an overlapping range. This is not a no overlap condition. It's a conflicting range, right? Because 3 and 5 and 1 and 4 conflict with each other. They do not overlap, or they do not belong to any of these two conditions, right? So it will call its both these children 5 and 2. Here as you can see start and end 3 to 4, this is a complete overlap of the queried range, right? This is this is this is completely inside the range which we want to query, so it will not make any recursive call. So let me do it. It will not make any recursive call to its children. It will return the result that is present in this node from here only. So 5 will get returned to 7, and it will be stored in the P1 of 7. 7 will now go to its right. Here as you can see, this is no overlap condition. This is out of bound, right, from the range we are querying. So 0 will be returned from here, and P2 it will be stored in the P2 of this 7. Now 7 will return 5 plus 0 to its parent node, which is 5. And finally the result will be returned as a sum of the elements present in this range will be 9 plus 5, this is 14. So if you will sum the elements which are present from 1 to 4, which is 3, 6, 1 and 4, you can see the sum is 14, which was returned finally by the root node. So this is how querying is done in a segment tree. Now let's talk about the complexity here. So I have taken a very small example here. So as you can see, I have to go through all the nodes, almost all the nodes. Only these two nodes, 1 and 4, they were not part of the calculation, right? Part of the flow. So it might seem like the complexity here will be big of n, but it's not the case actually. The complexity for this query operation is again log n, because if you will think about it, right, maximum number of recursive calls that will happen at a level. By level I mean this is an level, this another level, this is another level. The maximum recursive calls that will happen from our level will be 4. because root node represents the complete range, right? So for most of the queries it will make recursive calls to both of these children, right? So mm, uh, almost every time, until unless you want to know the sum of whole array, uh, these three nodes will be queried. Similarly, here as we saw, this was also a conflicting condition, this was also a conflicting condition, so both the children were called, right? But here as you can see, the 5 did not make any recursive call. Similarly 6 did not make any recursive call. So once you go to a depth of 2, the recursive calls that can happen at any level is almost 4, because if you will think about it, there will be only 3 cases for a node, right? So let's say we want to query from, for example, for this particular query, we want to query from index 1 to index 4. Now, if either a node will have a conflicting case, a node will be a complete overlap, which is our second condition, or the ranges will not have any overlap. So in any case, the two nodes that will be making recursive calls to their children, the nodes between them at the level will always be having a full overlap, right? Which is our second case, because if your starting index of your queried range, which is 1, that is present somewhere, let's say, that is within the range this node represents, and let's say the last index of your queried range, which is let's say 4, that is, let's say, present within the range this node represents, right? Then all the nodes that are present in this level to the right of this node, and all the nodes that are present in this level to this left of this node, they are out of bound, right? So they will be making the first condition true, and they will be returning 0 from them. Similarly, all the nodes that are present in between this node and this node, within these two border nodes, they will have a complete overlap situation, because no matter what the value of no matter what the range a node represents, it will always be overlap, because your first index and last index that you want to query is present within this node and this node. So the nodes between these two nodes in this particular level, they will be representing the range between these two ranges, right? So they will always have a complete overlap. So they will be returning from our second condition, and they will not be making any recursive calls. So the maximum number of recursive calls that can happen from a level are 4. So maximum number of nodes that will be queried at a level will be 4. So hence the complexity of this operation is 4 log n. Again, we remove constants while calculating the complexity. So the complexity become big O of log n. So this is all about operations in a segment tree. This video has become quite large, so let's quickly go to all the real life applications of the segment tree. So segment tree is used in leaderboards. So in gaming scenario, you usually see the leaderboards, right? Who's in the top, and they constantly get updated based on the scores a player get. So to update that leaderboard, segment trees are used. So they represent top scores in a range, average scores between ranks, updates a player's score in real time. They are used for all these purposes. Usually queries that are made in leaderboards are minimum, max, and average in a range, or we want to update the player's individual scores, right, within a range. So for all these purposes, segment trees are used. So result the internal nodes, they store generally the sum, max, and minimum or min count of the scores of the player, and they are used for all these range based queries and updating the scores of the player. Similarly, in image processing and computer graphics, uh, there is a range based queries happen to analyze the brightness and all those things of an image, right? Or updating the pixel of an image within a rectangular area. So here the 2D segment trees are used. So 2D segment trees work in a matrix. So this segment tree is a 1D segment tree which is representing a one-dimensional array. To represent a 2D array which is a matrix, you use 2D segment tree. So this is an advanced version of a normal segment tree. There are 2D segment trees, 3D segment trees, and so on. So they are a bit more advanced and their operations are a bit more complicated than this segment tree. They are used while updating multiple dimensional data or querying multiple dimensional data, and they are quite efficient in that process as well. The complexity is again log n for them. So segment tree is also used in stocks and trading platforms where we want to show a min max stock price in a particular date range. We want to update the price as they come down or go up, and entries there are in millions, right? We have a huge data, so entries there are in millions. We have lots of analytics to run as well, right? So segment tree is used to store the price within each node, holding the min, max, or some whatever is needed accordingly. They will store the result. They update the price in order of log n time, and they are very fast for querying the data and everything. Okay, that is all for today's video, guys. Thank you for watching. Please like, share, and subscribe my channel.